Classification of crystalline solids. Based upon three-dimensional arrangement. Based upon 3D arrangement. Earlier we have seen classification of crystalline solids based upon type of interaction. If the interaction is electrostatic interaction, we call them as ionic solids. Covalent interactions, covalent solids. Metallic interactions, metallic solids. Whereas van der Waals interactions, molecular solids. Now this is based upon three-dimensional arrangement, we are classifying crystalline solids. Right. Now what do you mean by space lattice?
Regular 3D arrangement of
Or crystalline lattice. So we can look at either space lattice or crystal lattice. So it is nothing but regular
3D
three-dimensional arrangement of lattice.
molecules.
Regular 3D arrangement of lattice points. What are lattice points?
Identical points arranged in 3D.
Lattice points are nothing but maybe ions or atoms or molecules. Right? Nothing but some identical points. Some identical points. Here we need to understand about another term called unit cell. Unit cell. Repetition of this unit cell produces space lattice. Repetition of this unit cell will produce space lattice. Now define what is unit cell. Unit cell means smallest, right away. Smallest three-dimensional arrangement of atoms or particles which on repetition produce space lattice. Smallest three-dimensional arrangement which on repetition produce
Space lattice.
space lattice. Now, before going to three-dimensional arrangement, let me discuss about one-dimensional arrangement. Right? One-dimensional arrangement. Of lattice points. One-dimensional arrangement of lattice points. Give me any one-dimensional arrangement of lattice points. See this? If I assume marbles or spheres or dots, so these dots are arranged in a regular fashion. Assume that they have uniform separation. Now we call this as one-dimensional. Now, how many parameters are required to express this one-dimensional arrangement? How many parameters are required? Only one distance parameter is sufficient. They are arranged in a regular manner. So they are separated by equal distance. So one distance parameter is sufficient to express one-dimensional arrangement. So one distance parameter is sufficient. Let me assume they are separated by a distance of a. Here also a, and so on. Right? So they are equally separated by a distance a. So one distance parameter a is sufficient to express them. Now see this. If I assume this is a center point between the spheres. Now, can I say this is the distance of separation between them? Let me assume that as a. So they are equally separated. Now what about this? This is also same. Here also they are equally apart. So both are nothing but one dimensional. Among these two one dimensional arrangements, which is more stable form of arrangement? First one. So this is more stable form of arrangement. More stable form of arrangement. Because it has low potential effect. This is less stable form of arrangement. And it have high potential. If they are apart, they require high potential. Right? So which is more preferred? This is more preferred form. So it is difficult. So always we have to prefer more stable form of arrangement, whether it is one dimensional or two dimensional or three dimensional. We prefer more stable form of arrangement. That means our potential energy must be low. Now coming to two dimensional arrangement of lattice points. Then we will go to three dimensional arrangement. Arrangement of lattice points. Now observe this. So this is one dimensional arrangement. Now if I bring another such layer, then what we call this as? This becomes two dimensional arrangement. This is two dimensional. Now how many parameters are required to express this? Between this and this. No, between this and this. And angle between them. Right? So we require two distance parameters. Two distance parameters A, comma B and one angle parameter. Let me So totally 3 parameters are required to express two-dimensional arrangement. Totally 3 parameters. 2 distance parameters, 1 angle. I may increase the distance between these two by providing some gap. Or I may increase distance between these two by providing some gap. Right? So let me assume this as a distance parameter A, parameter B, and angle parameter alpha. So totally 3 parameters are required to express it. Now, observe this. This is one-dimensional arrangement.
Yes.
Now I am bringing another such arrangement below this, but observe this case. Observe the first condition and this condition. Have you found any difference here?
Yes.
There is a small change in arrangement. This is the third layer. This third layer is matching with the first layer. Right? This is also two-dimensional arrangement, but this differs from the first case. Correct?
Yes.
This is also two-dimensional arrangement, but it differs from that case. So this is called as square type of pattern because it is forming some sort of square way of arrangement. Right? So we call this as square pattern. We call this as square pattern. We call this as hexagonal pattern. That is a square packing. This is hexagonal packing. Here also I require same 2 distance parameters and 1 angle parameter. So for any two-dimensional arrangement, I require 2 distance parameters and 1 angle parameter. So distance parameters A, comma B and angle parameter, let me assume that as alpha. That is sufficient. Now observe. Can I construct a hexagon here like this? So as I am capable of constructing a hexagon, that's why we call it as hexagonal pattern. Or we can also make a triangle. Can I construct triangles here? Right? So we can construct a triangles, we can construct a parallelogram, right? So if this is the case, we can construct a parallelogram, or we can construct triangles. So square packing, hexagonal packing. Now, so let me make some discussion about how the packing efficiency, what is the unit cell and so on. Right? If I consider square as the unit cell, here I am assuming this is square as the unit cell. What is my unit cell? Repetition of this will construct this total lattice. Right? So repetition of this square is constructing the lattice. So I am considering this as unit cell. this as the unit cell. Here I will assume this hexagon as the unit cell, or I can assume parallelogram as the unit cell, or triangle as the unit cell. Here I am assuming hexagon as unit cell. No. For this, number of nearest neighbors. I need to calculate number of nearest neighbors. And how many nearest neighbors is this? If I consider this as one lattice point, I am assuming this as a lattice point. How many nearest neighbors for that lattice point? Now here if I assume this as a lattice point, how many nearest neighbors for this lattice point? Now what about number of nearest neighbors here? How many number of nearest neighbors here? Number of nearest neighbors equal to 6, because from here 1, 2, 3, 4, 5, 6, right? And each one separated by a distance. Let me assume the distance as a. Let me assume distance between these two as a. So each one is separated by a distance a. Now here number of nearest neighbors are 4. Let me assume the distance of separation here also as a. So I am assuming this distance as a. Distance a. Now, number of next nearest neighbors means second nearest neighbors. Number of next nearest neighbors. Calculate. Next nearest neighbors, or we call them as second nearest neighbors. Next nearest neighbors means nothing but second nearest neighbors. How many second nearest neighbors? Calculate. Now, see this? For this sphere, this is the first nearest neighbor. What about this sphere? What about this one? If this is the first nearest neighbor, what about this one? This will be the second nearest neighbor. Right? Now, how many such second nearest neighbors? How many such second nearest neighbors? 8.
5.
So this is one. What about this distance? Can I say that distance as root 2a? This is a. What about this one? This is also a. Then what about this one? Root 2a. So that forms a triangle. Answer this. If this is one sphere, second sphere, third sphere, fourth sphere. This distance is a. This is also a. Then what about this distance? It forms a right angle triangle.
Yes, sir.
Then this is hypotenuse. Right? Square of hypotenuse is equal to, if I consider it as x square is equal to a square plus a square. So x square is equal to 2a square. X is equal to root 2a. Right? So second nearest neighbors are separated by a distance of root 2a. How many such second nearest neighbors are there? If it is a two-dimensional. This is root 2a. What about this? What about this one? Same root 2a. So 1, 2. What about this? 3, 4. Anything else?
No.
Right? So second nearest neighbors are Second nearest neighbors are 4. Second nearest neighbors are 4. Now what about second nearest neighbors? Second nearest neighbors. See, this is first nearest neighbor. This is also first nearest neighbor. What about this one? That is the second nearest neighbor. Now, what is the distance between these two?
2a.
No. This is A and this will be 2A. A and A. This will be 2A. What about this one? Is it closer than this or not?
Yes.
Compared to this is closer. So, this is the second nearest neighbor. So, what is the distance? This is the second nearest neighbor or not? If I consider this forms some parallelogram.
Yes, sir.
Like this, no? This is a triangle here and this is a triangle here. This is twice the height of triangle. And what is the value? What is the height of a triangle? What is the value for the height of a triangle? Root 3a by 2. If a is the base, if this is a, then what about this height? If this is also a, this is also a, then it is an equilateral triangle.
Yes.
For an equilateral triangle, height is equal to root 3a by 2. This is the height of an equilateral triangle. Then what about this one? This is also root 3a by 2. Then what about this total distance? Root 3a. So, second nearest neighbors are at a distance of root 3a. Right? So, distance between these two is root 3a. Distance between the center and this side is root 3a by 2. Because this forms an equilateral triangle, no? This forms an equilateral triangle. And this is another equilateral triangle. So, this is the second nearest neighbor for this. This value is root 3a by 2 and this is again root 3a by 2. Total between these two distance is root 3a. Now, how many such second nearest neighbors? How many such second nearest neighbors have I?
3.
Can I say this is on the back side of this side. This is side of this hexagon.
Yes.
So, for every side you have one such sphere.
Yes, sir.
Correct? So, how many sides are there? 6. So, number of second nearest neighbors are 6. Now tell me, what about number of third nearest neighbors for this? Number of third nearest neighbors at a distance of, yes,
4.
means 2a. Right? So, how many such second nearest neighbors are available?
8.
How many is third nearest neighbors at a distance of 2a? A and this is again another a. So then this will be 2a. So 1, 2, 3, 4. Number of fourth nearest neighbors?
4.
No. Fourth nearest neighbor will be different because you will have fourth nearest neighbor here. So this is first, second, third. This will be the fourth nearest neighbor at a distance of.
At a distance of root 4 and 2, root 2.
Huh?
2.
This distance is 2a.
2a.
This is a. Then what about this distance? Well, from here to here, the distance is 2a. This is a. Then what about this distance? Root 5a. So at a distance of root 5a, how many such neighbors are there? 1, 2, 3, 4. That means on every side you will have 2. On every side you will have 2. So totally 8 third nearest neighbors at a distance of root 5a. At a distance of root 5a, you have 8 third nearest neighbors. So let me stop here up to second nearest neighbor. Right? Next. What is the space occupied by each unit cell? Space occupied by each unit cell. What is the space occupied by each unit cell? This is unit cell. What is the space occupied? A square. It is not perimeter. Area. Right? Space occupied by each unit cell is nothing but area. This is 2 dimensional. That's why we are calculating area. If it is 3 dimensional, we will calculate volume. Right? So space occupied by each unit cell is nothing but A square. Now what about space occupied by each unit cell here? What is the space occupied by each unit cell here? Here I am assuming hexagon as the unit cell. If I assume triangle as unit cell, then area of triangle will be the space occupied by unit cell. If I assume parallelogram as unit cell, then that will be different. Here I am assuming hexagon as the each unit cell. Then what is the space occupied? Can I say 6 into area of equivalent triangle? 6 into area of equivalent triangle. Are you able to understand? This is equivalent triangle. How many such triangles are possible? 1, here 2, 3, 4, 5, 6. So 6 into area of equivalent triangle. Now what is area of equivalent triangle? Area of equilateral triangle. Half into base into height. Formula for triangle formula for area of triangle. Area of triangle is half into base into height. Correct? So if I consider this as equilateral triangle, what is the base length? What is this base length? A. What is this height value? Just now we have seen. What is the height value?
Root 3a.
Root 3a by 2. Right? So what is area of equilateral triangle? Half into base value into height value. Root 3a by 2. So what is the total value? Root 3a square by 4. How many such equilateral triangles are possible in this hexagon? 6. So 6 into root 3a square by 4. So can I cancel this? 2 3's, 2 2's. So what is the value now? 3 root 3 a square by 3 root 3 a square upon 2. That is the area of unit cell, each unit cell. Next. What is the space occupied by spheres in unit cell? Space occupied by spheres. Here I don't call it as spheres, we call them as circles. Right? So space occupied by circles in each unit cell equal. Here also it is 2 dimensional, so here also space occupied by circles. Here these circles are nothing but lattice points. Circles are the repeated units, no? So circles are the lattice points, right? So these circles are nothing but lattice points. So space occupied by circles in each unit cell. What is that? What is the space occupied by circles? What is the share of this circle for each unit cell? This circle lo enta share undi unit cell. What is the share of each circle in each unit cell? 1/4. How many such 1/4s are there? 4. Means 1. So what is the space occupied by circle in each unit cell? Means 1 circle. What is the value of that circle? Area of circle is pi r square. So can I write pi instead of r, can I write a by 2 whole square? This is a. So what is radius? Means a by 2. Here radius is equal to a by 2. So pi r square. Instead of r square, I am writing a by 2 whole square. Now what about here? How many such circles are there? 6. What is the share of this circle? 1/3. 1/3 circle. This is 120 degrees angle. So 1/3. So 1, 2, 3, 4, 5, 6. 6 1/3. 2. 6 1/3 is 2 and 1 circle here. Totally 3 circles. Right? So 3 circles means 3 into pi r square. Instead of r, a by 2 whole square. And what is this value now? This is nothing but equal to 3 pi a square by 4. Here this value is pi a square by 4. This is the space occupied. This is the space available. Can I call this space occupied as space available in each unit cell? This is space occupied in each unit cell. This is nothing but space available. And this is space occupied. In each unit cell, this is the space available. And this is the space occupied in each unit cell. Now what is the space empty? What is the space empty? What about empty space? This space is empty, no? This total, this gap is empty. So what is that empty space value? Can I subtract this two?
Yes,
that is empty space. Right? So packing fraction. Packing fraction. Packing fraction means space occupied upon space available. Packing fraction means space occupied upon space available. Now what is space occupied? What is space occupied? Pi a square by 4. Space available? A square. So if I divide both, what is the value left? Pi by 4. So packing fraction is nothing but pi by 4. This is nothing but equal to 0.7. Pi by 4 is nothing but pi means approximately 3.142 divided by 4. 3.142 approximately 3.142 divided by 4. 0.74 is 28. 28 means 29, 30, 31, 3, 34. 7, 8 is 32. 32 means again 2 left. 22. 5 is 20, 5 is 20. So 0.7855. 0.78. Approximately equal to 0.7. So can I say, based upon this, 78% of space is occupied. Space occupied by space available is nothing but 0.78 means 78% space occupied. Right? So that is 78% space occupied. Now what is empty space? 22% space is empty space. We call that empty space as void. What we call it as? Void. So 22% space is void, 78% space is occupied. Now what about here? What is packing fraction here? So packing fraction is space occupied upon space available. That means the space occupied by space of unit cell. Right? Space occupied by lattice points upon space occupied by unit cell, or space occupied by space available. What is the value? 3 pi a square by 4. This is space occupied by lattice points. Divided by, this is space of unit cell. 3 root 3 a square by 2. What you get? A square 1. 2 ones, 2 twos, 3 1. So pi by 2 root 3. So packing fraction is nothing but pi upon 2 root 3. What is this value? This is approximately equal to 0.91. What is the value? 0.91. That means, what is the meaning of it? 91% space occupied. So what about empty space? Void. 9% space is empty. Now among these two, where circles has occupied space available efficiently. In both cases, both are two-dimensional. In both cases, where circles occupied the available space more efficiently. So among these two, which will be readily possible arrangement? Hexagonal arrangement is readily possible. Which is more stable arrangement? Hexagonal arrangement is more stable, right? So that means nothing but if we have a carom board, we keep on arranging carom coins in carom board. In which way we need to arrange them to occupy more efficiently? Hexagonal way we need to arrange, right? So we have to discuss about three-dimensionality.